Hi everyone, welcome back to Data Cadence. My name is Rahul. I work as a senior applied research scientist, and in this video, we are going to have a look at some of the most important metrics for evaluating time series forecasting models. Now, when evaluating time series models, it's crucial to select the right metrics to assess their performance effectively. Each metric can reveal different aspects of a model's accuracy and suitability for a particular task. So in this particular video, we'll cover the most commonly used metrics, their mathematical definitions, the pros and cons of each of these metrics, and when it's best to use each one of these. So like every other video, we will go into a lot of depth and we'll try to cover each one of these. It might be a refresher for a lot of you who have prior understanding or have basically used these metrics in the past in some of their projects. So it would be a good refresher for those. And for those who are new, it's also a very important interview question, especially if you have worked or have some sort of background in time series forecasting in your previous organizations. So without further ado, let's begin. So let's start with the first metric, that is mean absolute error. So MAE measures the average magnitude of the errors in a set of predictions without considering their direction, and it is calculated as the average of the absolute differences between the predicted and the actual values. So you can see that MAE is given as 1 over n, summation over all the data points from 1 to n, the actual value minus the predicted value, the absolute modulus of that. And what are some of the pros of, and of course why I had refers to the predicted value, like we use the standard notation, and why I here is the actual value in your time series. When we talk about the pros, so it's pretty simple to understand and also to interpret. So it's pretty intuitive when it comes to interpretation, and it is robust to outliers in the response variable. So if the response variable or the target variable that you are trying to forecast has outliers, so it is pretty robust to that. When it comes to the cons or the disadvantages, it does not penalize larger errors significantly like some of the other errors do. We'll have a look at them. It does not give information about the direction of the error. So that is another thing. So whether we are overestimating or we are underestimating, that kind of information is not being given by MAE. And it might not be suitable for data where scale of values change significantly over time. And when is it best to use MAE? So when you want a straightforward, understandable metric that reflects the average error size, so it's best to use MAE in such scenarios. Let's talk about the second one, that is say MSE, or mean squared error. And MSE basically measures the average of the squared differences between the predicted and the actual values. It emphasizes larger errors due to squaring, which makes it more sensitive to outliers. And it is given as 1 over n, summation from I equals to 1 to n, yi minus yi hat squared. It's pretty straightforward. If we talk about some of the pros, so it's widely used in regression problems, and in fact all of these metrics will also be used in a lot of the regression based problem statements, because time series and regression are two very similar problem statements. The time series have a dependence over the time. That is one of the major differences, but yes, all of these metrics also hold for regression problems. So let's get back to this. So the second one is it's differentiable, which makes it extremely useful for optimization during model training. And when we are talking about differentiability, so MAE or mean absolute error is not differentiable, which is another drawbacks which makes it basically not very useful when you want to do some sort of optimization using techniques like gradient descent and all. So that is the second advantage here. And the third one is it heavily penalizes larger errors, making it suitable when large errors are particularly undesirable. So that's another advantage for the mean squared error. When it comes to cons, so the first one is it is sensitive to outliers, which can disproportionately affect this particular metric. And the second one is the squared units of the error make it less interpretable in practical terms. So say for example, you are trying to forecast the cost of something, and if you get your error as dollar squared, or when the units are say dollar squared, that makes it really less interpretable in practical terms, and it makes it harder to explain as well. So these are some of the disadvantages. And when it comes to when to use MSE, so we can use MSE when large errors need to be penalized more heavily. So that is one scenario where MSE might be a favorable choice. The next one is RMSE, or root mean squared error. So RMSE is the square root of the MSE. It maintains the same units as the original data, which makes it even more interpretable than MSE. And like we see, it's given as square root of 1 over n, summation I goes from 1 to n, yi minus yi hat squared. And like we said, in terms of pros, it has the same units as the original data, which makes it very easy to interpret. And like mean squared error, it also penalizes heavy errors more severely because it also has that squaring term. When it comes to cons, so it is still sensitive to outliers due to squaring of the errors, and it may not provide meaningful information if the scale of data varies significantly over time or across different data sets. So when to use RMSE? When we want to penalize larger errors and maintain the same units as the data. In such a scenario, RMSE is one of the most important metrics, and in fact it's one of the most commonly used metrics when it comes to evaluation of time series forecasting models. Let's talk about the fourth one, that is mean absolute percentage error, or MAPE in short. So MAPE measures the average absolute percentage error between the predicted and the actual values, and it's useful for understanding the error relative to the size of the data. And MAPE is defined as 100 over n, summation I goes from 1 to n, yi minus yi hat over yi, and it provides a percentage error which is easier to interpret and useful for comparing model performance across different datasets. That one of the best advantages when it comes to MAPE, and it scales naturally with the magnitude of data, making it useful when the absolute scale of prediction changes. When it comes to the disadvantages, so it is undefined when the actual values are zero, because in the denominator you will end up with a zero, and that's why it will become undefined. And the second disadvantage is it can be heavily skewed by very small actual values, resulting in disproportionately large percentage errors. And that is one of the drawbacks of MAPE. So when to use MAPE? You can use MAPE when you need to compare the error relative to the size of the data, and when actual values are consistently non-zero and of a similar scale. In those scenarios, MAPE would be good. The next one is sMAPE, or symmetrical MAPE, which tries to address some of the limitations of the vanilla or the plain version of MAPE. So sMAPE is given as 100 over n, summation I goes from 1 to n, yi minus yi hat, and then on the denominator you have the average of your actual value and your predicted value, that is yi plus yi hat over 2. And it symmetrically penalizes both the overestimation and the underestimation by using both actual and predicted values in the denominator. And when it comes to some of the advantages, so it reduces the risk of skewness due to small actual values when compared to MAPE, and it also provides a more balanced metric which is less sensitive to outliers. When it comes to the cons or the disadvantages, of course, it is more complex to interpret than MAPE, as it doesn't represent a simple percentage error, and it can still produce misleading results when the actual values are near zero. So when to use sMAPE? You can use sMAPE when you need a percentage based error metric that is less sensitive to outliers and extremes of your actual values. And let's talk about the next metric in our list, that is say R squared. And R squared basically measures the proportion of variance in the dependent variable that is predictable from the independent variables. And for time series, it is often used to assess how well a model captures the variance in the particular data. And R squared also is very popular metric in regression based problems as well. And it is defined as 1 over summation I goes from 1 to n, yi minus yi hat squared, divided by I goes from 1 to n, summation of yi minus y bar whole squared. And y bar is basically the mean of all the actual values. And when it comes to the pros, so it's pretty intuitive, providing a percentage that explains how well the model explains the variance in the data. And like I mentioned, it's pretty commonly used and easily interpretable in the regression context. When it comes to disadvantages, so it's not suitable for non-linear models or non-stationary data where the assumptions of linear relationships are not met. And it can be misleading if the data contains outliers or if it does not properly account for the seasonality and trends which are typical of time series data. So when to use R squared? So you use R squared when dealing with linear models and stationary data where understanding the proportion of explained variance is beneficial. So these are some of the metrics that we saw when it comes to evaluation of time series forecasting models. And if I were to conclude, so selecting the appropriate metric for evaluating time series model depends on the specific characteristics of your data and your goals. So for instance, MAE and RMSE are useful for straightforward, easy to understand evaluations, especially when handling models where errors need to be penalized differently. MAPE and sMAPE provide percentage-based errors which are helpful when comparing performance across different datasets. And R squared gives insights into variance but should be used cautiously with non-linear or non-stationary data. So choosing the right metric often involves considering multiple metrics to get a comprehensive view of the model performance. And it's important for you to know about all of these metrics if you are working on a time series forecasting problem. And also it's an important interview question in case you have worked on time series data in the past, or even if you have some basic understanding about time series or regression in general. So hopefully this video gave you a lot of insightful context or a quick refresher, whatever it is that you're looking for before an interview, and hopefully it provided some more help in your journey of preparation. So if it did, please consider pressing the like button, and thank you for all the love and support that you have shown towards the channel so far. I do have plans on bringing more such important content and trying to cover things in depth and as much in depth as possible. So do subscribe to this channel for more such content, and I will see you in the next video. Till then, take care, stay safe, and keep learning.